We are on to graphing exponential functions. And in this case, I happen to have written them all as y equals, but I could just as easily write them as f of x equals. So I'll call them functions, same thing. And let's just see what one of these might look at. So I've kind of started with the most basic one we can come up with, y equals 2 to the x power. So as we do sometimes when we're trying to figure out sort of the basic shape of these, let's just do a little xy table here. And of course, negative exponents are a thing. So I'm going to start with, -0. Good. Okay. 0. I'm going to start with negative numbers, and then we'll go into some positive numbers here. All right. So 2 to the -2 is 1/4. 2, you might remember that thing with the 4s from some other video that we did here, but 2 to the -1 is 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. So let's see what this looks like when we graph it. Again, I'm going to be a little freehand about this. So -1, -2, 1, 2. Okay. So when x is -2, y is 1/4, so very small. When x is -1, y is 1/2, still pretty small. When x is 0, y is 1. I guess I'll put some marks here. X is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. So we can actually see a pretty clear shape here. And, I'm going to, just to see what happens over here, but what if we put in x equals like, -5 or something like that? Okay, so 2 to the -5th power is 1/32. So we go way over here. So 2, 3, 4, 5, just like right there. So we can see what's happening here. It's not crossing the x-axis. It's just getting very close to it. And then as we move along here, it's curving up and up and up like so. And that's going to be sort of the general shape of any basic exponential graph. And what I want to point out is that there are 2 points on here that are sort of going to be the easiest to find in most cases. There's a point where the exponent equals 0. And we're going to have when x is 0, y is 1. Because anything to the 0 power is going to be 1. If this were 5 to the x, when x was 0, y would also be 1. So that's going to be a pretty common point. So that's there. And then we have this point here, 1, 2. In other words, when the exponent is 1, anything to the first power is itself. So if we had y equals 5 to the x, then when x was 1, y would be 5. So we kind of have these like 2 standard points, 0, 1, and 1, whatever the base is. In this case, the base is 2. And these are going to be 2 really fundamental points to help us graph exponential functions in general. So let's look at another example. Similar, except instead of 2, now we're graphing y equals 1/2 to the x. So, well, let's see what happens. Let's start with those 2 points that we just talked about, 0, 1, and 1, whatever the base is. Okay, so I'll put a couple marks in here again. 2, 3, 4. 1, 2, 3, 4. Okay. 0, 1, throw that in there. 1, base. So when x is 1, y is going to be 1/2. So we can make a prediction about what's going to happen here. But just to make sure, let's put in a couple more points. Let's do x equals -2. 1/2 to the -2. Okay, that would be the same as y equal, there's sort of a long way and a short way to do this, but let me write it this way. I'll be a little clever about this. That's 2 to the -1 to the -2. So that would be the same as, I could multiply those, 2 squared equals 4. Okay, so I can put in x is, what was I doing? X was -2, y is 4. And then I'll try also with x equals +2. So I'm just plugging a couple more numbers in here just to see. So that would be y equals 1/4. So when x is 2, y is 1/4. And what probably was our guess is confirmed here, that it's going to be the same thing, but just going in the opposite direction. So it actually is high on the left and low on the right. So in terms that we've talked about before, this is like exponential growth because our multiplier, our base is bigger than 1. This is exponential decay because our base or our multiplier is less than 1. Okay, so there's a couple of basic exponential graphs. Let's keep this going a little bit. And we know we've got this general format, y equals a b to the x. So let's, pardon me, to the x power. So let's graph something that's in this format. And again, we kind of want to have these basic points. We want to have this point where x equals 0, or where the exponent is 0, and then where the exponent is 1. So here, okay, we can do 3 to the 0 power is 1, and then that times 2 is 2. I could really just write these as points, but it's fine. And then when x is 1, 3 to the 1 power is 3. 3 times 2 is 6. So let's put these points in. When x is 0, y is 2. And when x is 1, y is 2, 3, 4, 5, 6, close enough. And we know that this is going to start right along the x-axis and go up like that. So generally, if a question asks you to graph an exponential function like this, these are kind of the 2 points that you want. You want a point where the exponent equals 1, pardon me, a point where the exponent equals 0, and a point where the exponent equals 1. Now, one thing that we really should talk about here, and probably should have included in these last couple, so I'll go back there. I mentioned here we can see that this graph doesn't actually cross or even touch the x-axis at any point. And if we kind of think about this here for a second, 2 to the x power. So could we ever get that to equal 0 or equal a negative? Well, I think we can see that 2 to the something power is not going to be negative. There's no number of times you could multiply or divide 2 and then somehow get a negative number. And there also isn't a way for this to equal 0. Like we could have 2 to the negative, 9. That's just going to be 1 over a very big number. It'll be very close to 0, but it's never going to reach 0. So what we have on the x-axis is an asymptote. And if you haven't come across that word before, let me first spell it. So we've got it on here. Asymptote. And an asymptote is a line that a graph gets closer and closer to, but never touches. And so what we're going to have here is we're going to have an asymptote. It's going to be, let me draw it in orange. And it's going to be on the x-axis. Anytime that you're graphing an exponential function or anything that has an asymptote, it should be included. A lot of times it'll be a dotted line. I just don't happen to be able to do that on my tablet here, but that should be included. That shows us that, that blue line will get closer and closer and closer to the x-axis, but it'll never touch it. And same thing here. So if we're really being complete about this, then we would put in the asymptote there. That blue line, as we go farther and farther to the right, it's going to get closer and closer and closer to that orange line, but it's never going to touch it. That's what an asymptote is. And you're going to find that on every exponential function graph. They're all going to have asymptotes. And later when we get into graphs of logarithms, they're also all going to have asymptotes. So back here on this one we were just working on, I'll put in here, and for now, all these ones that we've had, the asymptote's the same at y equals 0. we'll see a couple coming up where that's going to be different. So this is our graph here of y equals 2 times 3 to the x. It goes through these two main points that we talked about earlier. So what if we just sort of talk about a general form of what I have up here? Y equals ab to the x. What is the general form of that going to be? Well, it's going to look like this. It's going to have one point at when x is 0. Okay, anything to the 0 power is 1. So this is going to be 1, and that's just going to be a times 1. So it's going to have a point at 0a. And then it's also going to have another point when x is 1. Anything to the first power, so b to the first power is b, times a is ab. So this is actually really useful because we could look at, let's say we got this graph and we didn't know its equation, but we were being asked to find its equation. We knew that it was exponential and we were being asked to find its equation. We would say, okay, well, what I know about graphs of exponential functions in this format is, they have these 2 points. When x is 0, y is a. Great, a equals 2. When x is 0, y is a. And I also know that when x equals 1, y equals a times b. So in this case, when x is 1, y is 6. 6 must be a times b. We know that a is 2, so b has to equal 3. And from that, we could actually put our function together. Y equals a, b to the x. So great, now we know how to graph this, but we also have this kind of neat thing that we can look at an exponential graph and actually pretty easily backtrack and find what the equation was. But for now, let's do a little bit more. Well, that's actually, I meant to use this page to show you that, but that's okay. That means we don't need this page. Let's look at a more complex version of one of these exponential graphs. So it's kind of the same thing that we were just doing, except now we have vertical and horizontal shifts. And of course, they're the same kinds of vertical and horizontal shifts that we've had in other graphs that we've looked at before, whether parabolas or radical graphs or absolute value graphs. Let's start with those. We have up here, x minus 3. We know that whatever context we see that in, set it equal to 0. So we have a horizontal shift of 3 to the right. We also have a vertical shift going 1 up. And it's this vertical shift that we're going to start with because this tells us what the asymptote, what the horizontal asymptote is going to be. So I'm going to put that in right at the beginning, that the horizontal asymptote for this graph, instead of being at y equals 0, it's going to be 1 unit up from that because the whole graph is shifted 1 unit up. If you're graphing this again, this should probably be a dashed line, but any way that we put it in is fine. And I'll label that as horizontal asymptote at y equals 1. Okay, so there's that. And we know that this whole graph is going to be shifted 3 to the right. And we've got a couple ways of dealing with that, but ultimately we're usually going to do these graphs based on 2 or 3 points. And we know that the points that are useful are exponent equals 0 and exponent equals 1. But of course, for this graph, that doesn't mean x equals 0 and x equals 1. We're talking about this is what we want the entire exponent to be. And so what we're really interested in is, okay, for the exponent to be 0, x itself actually has to be 3 here. And then for the exponent to be 1, x itself would need to be 4. And so these are the values that we're actually interested in. And this makes sense because normally we'd be interested in values here. We know the whole graph is shifted 3 to the right. And so now we're interested in values that are 3 to the right over here. So let's get our actual values for these. So when x is 3, exponent is 0, 4 to the 0 power is 1.
1 times a half is a half, and then plus 1 is 1.5 or 1.5. I'll put 1.5 there. And then when x equals 4, so 4 minus 3 is 1, 4 to the 1 is 4, 4 times 1/2 is 2, and 2 plus 1 is 3. So we have 2 points that we can graph here, 3, 1.5, and 4, 3. So let's put those on here. 3, 1.5, and 4, 1, 2, 3. Okay, 4, 3. And if we know the general shape of an exponential graph, then these 2 points will be sufficient to graph. So let's see if I can do this here. So we know we're going to start along the asymptote. Okay, we're coming up. And then as we reach these points, it's going to start curving upwards. And so again, what we did was we put the asymptote in to account for the vertical shift. So we know we're not going to cross that. We found, in this case, the values of x we needed to make the exponent equal 0 and to make the exponent equal 1. Plugged those in, found our 2 points, and then by knowing the general shape of the graph, we were able to graph pretty accurately from there. And of course, you can always put in additional points, but if you know the shape of the graph, as with the other graphs that we've done, then that'll save you the time of having to try another point and another point. The asymptote and 2 points should be sufficient to graph these pretty accurately. So let's do one more of these. And of course, there's a little bit of a twist in this one. So we know that vertical shift is down 2. And I'll go ahead and just put the asymptote in there at y equals -2. All right, that works. And I'll label that. So horizontal asymptote at y equals -2. Okay. And we know that to get the horizontal shift, we're going to set this equal to 0. Now, you notice it looks a little different because it's not x minus 1, it's 1 minus x. The x is actually negative. So this is going to affect things, but for now, I'll add x to both sides here. Okay, so we know that the horizontal shift is 1 to the right. Take a moment as you're watching this video and just make a prediction about what this is going to do. And as a possible hint, you could think of what would happen if we wrote it this way and what that would do to the graph. But let's see. We are going to follow our usual process here. We want to find the points where the exponent equals 0 and where the exponent equals 1. And for a more complex version of one of these, let's say the exponent, let's say it was like, 2 times 3 to the 4x minus 6. You're not going to probably get one of those. But if you wanted these two values, you could set 4x minus 6 equal to 0, solve, and figure out what x value that would be. And then set 4x minus 6 equal to 1, solve, and figure out what x value that would be to get the overall exponent to equal 0 and the overall exponent to equal 1. So that we'll sort of do something like that here, but that could come up if we had a particularly complicated one. In fact, let's do that just because the negative is kind of weird. So we want 1 minus x equals 0. That would give us x equals 1. Okay, so that's going to be one of our points. And then we want the exponent to equal 1. So 1 minus x equals 1. Okay, so the points where the x values we're going to plug in are actually 0 and 1, but just not in the order that we'd expect. So again, let's see what happens with this. When x equals 1, okay, 1 minus 1 is 0. 3 to the 0 power is 1. 1 times 2 is 2. 2 minus 2 is 0. So we've got a point when x is 1, y is 0. Then we have this point when x equals 0. 1 minus 0 is 1. 3 to the 1 is 3. 3 times 2 is 6. 6 minus 2 is 4. So when x is 0, y is 4. All right, so let's see what we've got. We can put in these 2 points. We've got 1, 0. X is 1, y is 0. And when x is 0, y is 4. So this looks different from our previous graph because the last one that we did, of course, the point on the right was higher. And now the point on the left is higher. Well, that combined with this negative x, a negative in that position is going to flip the graph horizontally. Remember, if we had a negative there, that would have flipped the graph vertically. This is different. This is in front of the x itself, and that's going to flip the graph horizontally. So we want to know that transformation, but also we can see it from where these points are and where the asymptote is. So again, we'll try to do a good job with the graph here. So it'll start along the axis, or pardon me, along the asymptote, and then follow the direction of these points going up. So that's not bad. And so what this negative sign does is it flips it horizontally. Instead of going high to the right, it goes high to the left. But again, if we know the general shape of the graph, we have the asymptote, we have these 2 points, we can actually kind of follow that and know where it's going to go. So those are kind of the basics of graphing exponential functions. We have our general format that we looked at earlier. And we know that if we're just graphing something like this, what we're really looking for is where the exponent equals 0 and the exponent equals 1. And then on a question like this, where the exponent's a little bit more complex, we are still looking for where the exponent equals 0 and where the exponent equals 1. It just, and this was a better example of it, it might not be at x equals 0 and x equals 1. It's whatever values of x are needed to make the exponent equal those things. And then between the asymptote, 2 points, those 2 points, and our general knowledge of the shape of this graph, we can come up with a pretty accurate version of what the graph should look like.